So now we're going to move on to computational complexity. So computational complexity is this idea I've been talking about for quite some time now. I started talking about this halfway through last semester when we were talking about things like the linear searches, right? How many things you kind of have to put your finger on. We didn't formally talk about anything. I just wanted to make sure you were aware of these ideas. And we also talked about these things when talking about some of those sorting algorithms, right? And some of these sorting algorithms were good. I mean, they're all good, I guess, but some seem to be a bit better than others. And in terms of, like, how are they better? What does it mean to be better? These are all these things that kind of come up when we talk about computational complexity. Yeah. This is where perhaps computer science can get a little bit more formal. Like, this stuff isn't really about the programming aspects, but it's a very important part of computer science. So, point of this lecture, what is computational complexity? How to analyze an algorithm's goodness, for lack of a better term. Is it a practical algorithm? What makes an algorithm good? Is your algorithm better than your friends? That type of stuff. So, I know when you're first starting to code, you don't really have a concept of, like, okay, well, what makes my algorithm good or bad? What makes one better or worse than the other? Like, if you wrote code and your friend wrote code, but you did it in 5 fewer lines of code, it doesn't really matter, right? You might think, mine's less code, therefore, no, it doesn't really. That really doesn't matter for a lot of what we would consider like our goodness metric, especially at this stage. The stuff we care about is, what are the resources needed? The algorithm needs some resources. But what are they? How much is it? Is it taking up a lot of resources, very few resources? Like, what about the CPU? Does it use a lot of CPU? Does it use up a lot of RAM? A lot of times these things can be at odds with one another. A lot of RAM, but it's fast. It's slow, but it uses very little RAM, that type of stuff. How many processors we're using, that could be another thing too, right? But that's usually a more advanced thing that we don't talk about until way later in your degrees. So, algorithm analysis. Often we want to know how much time your algorithm is going to take relative to the input size. The reason I'm emphasizing this, not only is it bolded, but it's also underlined, because it is so important to emphasize, it's not really about the absolute amount of time your algorithm is going to take. It's more about how much work is going to have to get done, how much work is this algorithm going to do relative to the input size, and as the input size grows, we often like to kind of keep that in our head too. So it's about how much work relative to the input size. We'll call this time complexity analysis. When we know how much time we expect a certain algorithm to take, it can help us choose the right tool for the job. Before I go any further in this lecture, this is going to still be, we're going to have another lecture near the end of the semester that's going to go into more detail about computational complexity. At this stage, I'm showing you the tip of the iceberg of the more formal stuff, so just be ready for that. There's a lot of other ways we can talk about complexity. We can talk about the memory complexity, we can talk about processor complexity, but right now, we like to focus on computational complexity. Other forms of complexity are important, really important things to consider, but we'll put a pin in that for now. So time complexity is based on the size of the input, the number of operations, and the number of operations, that's like units of work, so that could be something like addition, comparison, etc., right? So these are really what we care about, is the size of the input and what are the operations being done. We want to know the relationship between the size of the input n and the time it takes to solve the problem in terms of t of n, where t of n is like this time function, right? So imagine I have this algorithm, and I know I've got this function t of n that says, I'm going to show you an example of this in a moment, but the function t of n, it's just like a mathematical function that if I know what n is, if I know what the input size is, I could tell you how much units of time that's going to take up, or how much units of computation that's going to take up, for example. So t of n is a function of n. This means that the amount of time taken will depend on n, the input size. So t of n we call the growth function, and here is an arbitrary example. 15n squared plus 45n. Completely arbitrary. If you're asking what's the significance of those numbers, they're pulled out of thin air type thing, right? But let's pretend that the amount of time, I give you a function, the amount of time it takes for that function to run, or the amount of computing required for this function. If I have an input size of 10, well, I just plug in those numbers, and then t of n, like that tells me how much time or units of computation it's going to take. So obviously, if I give you 10, this is going to give you a number, but if I give you 20, this will give you a bigger number, right? As n grows, so does the so does the amount of time required. And if it wasn't obvious, yes, I'm still sick. How did lab go yesterday without me? Pretty good, yeah? Well, for those of you who have lab today, I won't be there. I won't get you sick, don't worry. Brandon will be, so still go, of course. But I won't be there because I don't want to give you the flu. Anyways, t of n, yeah. So there we go. As n grows, so will the amount of time it takes to grow. But then the question, of course, becomes, well, as n grows, how much does the amount of work grow? Like, as n grows, right, by how much does the amount of work grow? Like, if I increase n by 1, like if n goes from 10 to 11, how much more work is there? Now, if we have this function t of n, that's really nice. I mean, it's kind of a silly question to ask. Like, how does it grow? Like, it grows like that function. It's literally that function. Like, plug it in. Like, I can plot this function. Imagine I plot, like, n versus t of n, right? As n grows, well, what's the shape of this function? Well, it's probably going to look something kind of like that. Why? Well, because we've got, like, a square in there. But this is, of course, for one where we already have t of n. It's not just some arbitrary function we're looking at or something. So don't worry about where this t of n came from. Somehow I magically have this t of n. I have this function that I happen to know that's the growth function of some function. Here's a table, the left column there, that's like n, right? I'm increasing n as I go down. And then what I've done is I've kind of broken up the t of n, which is 15n squared plus 45n, into its pieces, right? And basically said, okay, well, when n is 1, 15n squared is 15. When n is 2, well, okay, and that's 4, 4 times so 60, okay, and so on. Then I also did it for the other part of the function, 45n. And then I did it for it all together, right? So I broke it down by each piece, and then the last column is, well, what's the total amount of work being done? So take a moment, look at this table. Just make some sort of observations. Take a minute, talk amongst yourselves. What do you notice about this table? Try to discover some properties about how these numbers are changing. Have a chat. Take your time. All right, what are some trends we see?
15n square growth is more compared.
No, say that again louder.
15n square growth is higher compared to 45.
I mean, as n increases, 15n squared grows way faster than 45n. This shouldn't blow anyone's mind unless you haven't finished grade 9 math, of course. We know squares will grow faster than linear things. So, as n increases, this grows way faster. Well, okay, look at this number. This is the combination of the two. Which of these two terms, this term or this term, makes up the bulk of this term?
15n squared.
This one, right? Obviously. Right? In fact, someone do a really quick calculation for me. Someone do like 45 million, like what proportion of this is this, right? Like 45 million of, what is this, 15 trillion, 45 million. Someone do that calculation really quick. Which proportion? Like what's the proportion there? 0.0003 percent. Oh, percent. So it's even smaller. So 0.000003. Whatever. The actual precise number isn't even what's important. The point is, it's small. And as n gets bigger, that percentage is going to get smaller and smaller because this is going to keep growing at a pace much bigger than this. The point of all that is, if I asked you the question, what term dominates, what would you say? 15n squared. Even though I've never even really formally introduced what the idea of dominates is, you had a good idea as to what it probably meant. In fact, I have plotted a couple things here. I have plotted 45n. So by the way, look at the axes. 0 to 10,000, I guess. And this is t of n, I guess. 0 to 1.4 times 10 to the 13, whatever. The 45n is, I mean, it's effectively a flat line. Even though it's clearly not, like it shouldn't be a flat line because it's linear. It should grow, you know, kind of like this. But as a consequence of the scales, because the growth of 15n squared is so much more rapid relative to 15n squared, that 45n, basically nothing, right? But I also, on this line, have plotted 15n squared plus 45n, the green one. But where, any idea where 15n squared is on this line?
On the
Same.
Same line.
Yeah, basically, the green and blue one are
Same.
the same. They're like on top of each other. Because that's the dominant term. As n grows, so a lot of times when we talk about these growth functions, in a moment I'm going to explain it in more detail. Computer scientists are really lazy. We don't like coming up with these growth functions. We like coming up with quick and dirty, simple ways to say it, where we'd be like, well, the amount of work being done, instead of getting precise and saying, oh, here's the growth function, we're going to say, well, it's going to grow like, and in this case I would be like, this function grows like n squared grows. That's what I would say. Because, I mean, the other terms don't even matter at all. They have like minimal effect. So when n was small, which part, like let me put it this way. Let's say n is 1. Which term was bigger?
45n.
45n. But that's just a consequence of like the small numbers. As n grows, and a lot of times we care about n when n is arbitrarily large. We like to think about it in terms of like, let's pretend n is like a bajillion. So as n grows, the 15n squared is clearly going to become more important. And at the end of the day, we really don't care about those constants. Because here's the thing. It's a constant. how does a constant change as n increases? It doesn't. It's a constant. It's like stuck, right? So imagine for a second, we go back to this plot. I've plotted 15n squared. What's the shape? I didn't draw it here. At no point is n squared plotted. 15n squared and 15n squared plus 45n is plotted. But if I gave you a marker and this plot, and I said, draw n squared on this plot, what would you draw it like? The 15n, it would basically look exactly the same, because that constant doesn't really have any weight on the growth. That's a key thing to remember. A lot of young computer scientists miss this point. It's about the growth. How does it change as n grows? And those constants, because a lot of people be like, but something that's like 10n squared is still going to be more than something that's 2n squared, because 10 is bigger than 2. Of course you're right, of course. But it's about the growth, and they both grow the same way. That constant, they're still just constants. Total absolute amount of work, yeah, fine, but it's the growth that we're really interested about. There's 1,000 asterisks applied to what I'm saying. It always depends on your certain situation. Yeah. So, since the n squared part is the biggest thing, and because the piece grows as n grows, we say that n squared is the dominant term. It's an important thing we like to say. It's the dominant term. And this is what I was talking about. We like to be lazy. Asymptotic complexity. We really don't care about the constants. We don't care about the non-dominant terms. We care about asymptotic complexity. It's a fancy way of saying the time the algorithm takes as a function of n will grow like n squared. With that t of n, it's going to grow like n squared. And this is where the big O notation comes from. I've talked about this before with never really introducing it. And don't worry, if you think this stuff is fun, you're going to get a lot more of this, a lot more rigorously in discrete math. You get a lot of it. Is anyone in here in discrete math right now? A couple people? Have you gotten to this yet, discrete math? No. So in our example of t of n, we would say order n squared. Big O, n squared. Worst case scenario type stuff. This is the O in big O notation. So putting it all together, the time the algorithm takes as a function of n will grow like n squared for this particular situation. Are there any questions about this? Now this is all fairly abstract at this stage. And raise your hand if you can't help but think, what does this have to do with like the programs I'm about to write though? Yeah, a bunch of people are going to kind of wonder that. People are going to wonder, okay, this is great and all, but we want to connect these dots. Don't worry, we'll get there in a moment. Let's do a real quick little quiz. I guess this one's not the quiz. I guess quiz will be on the next set of slides. T of n is 17. What does 17 grow like? How does that T of n grow as n increases? It doesn't. It always takes 17. If n is 1, it takes 17. If n is a billion, it takes 17. Great. For that, we say it's order 1. That means constant. If t of n is 20n minus 4, n. Why? Well, because who cares about the constant? Who cares about the lower powered term? In this case, n to the 0, I guess. 12n times log n plus 100n. This one might throw you off a little bit, but really we see 12n times log n. That's like one term. Okay, so there you go. As n increases, it's going to grow like that. 3n squared plus 5n minus 2, n squared. 2 to the n, that's a bad one. If you write an algorithm that's 2 to the n, you're in trouble. We've got, so I don't have it here, but probably by the end of the class, I'll go to the Wikipedia page. The Wikipedia page includes a more exhaustive list of the different computation complexities we typically look at. We can have a whole bunch, but there's fairly typical ones, and especially at this stage, the ones we're going to see will be like order 1, n, maybe log n. Log n is worse than 1, but better than n. N log n is worse than n. And then n squared is worse than those. And so on and so on and so on and so on and so on. But if you see something that's 2 to the n, that's like one of the worst you can, like, that's horrible. You don't want that. But here's the thing, and I should emphasize this. There are some problems out there where perhaps a really good solution to that problem, there are some problems out there where maybe the algorithm to solve that problem is like 2 to the n. Okay, and it's like, well, tough, there you go. That's how long it takes. And that's bad because as n grows, it's going to take longer than like the universe has existed to solve. But keep in mind that like the problems and the algorithms, they're independent things. You know what, more on this later in the course. Let's not get too bogged down that right now. If I plot these things, this is what we would see. Of course, constant is not shown, it would just be a straight line. So of the ones plotted here, which is the worst? N cubed. What's the best?
Constant.
Well, yeah, constant, yeah. But of the ones shown, I guess it's the linear, order n. N log n, it's worse, but not as bad as n squared. These are fairly common ones we'll come across. So a quick test. When you look at that first one, on the count of 3, everybody yell out the, oh, yeah, you have a question.
Yeah, is log base 2 a lot more common here than log base 10?
Oh, let me clarify, yeah, almost always this is going to be log base 2. And the reason is, because we'll like, there's a lot of reasons, but a lot of times it's because we'll do kind of a strategy called divide and conquer where you can eliminate half the things. So it's like divided by 2, divided by 2, divided by 2, divided by 2. So that's why it's always log base 2. Yeah?
I'm a bit confused. Why is n less than n cubed? Are we looking for the one that goes the most? Or
No, oh yeah, pardon me. Great question. We want to minimize the amount of work done. We want an algorithm that's going to require the least amount of work. All of this, let me help start putting context to this. If you had a problem to solve, and one of you on your assignments gave me a solution that was order n, and another person came along and gave me one that's n squared, the order n one is better. Unless the goal was to come up with a slower algorithm, the order n one, that's the one we want. Great point, because yeah, you might assume like, why, like look, it's bigger, better. No, we want smaller in this case. Great question. All right, quiz time. On the count of 3, everybody yell. What would the big O be? 1, on the first one. 1, 2, 3.
N squared.
Good. Now look at this next one. Okay. On the count of 3. 1, 2, 3.
N cubed.
It is n cubed, but I heard someone say log something, and let's clarify. A lot of times we can simply like break them up by like your additions and subtractions. It's the multiplies that put the terms together. The additions is what kind of like separate the terms. This will become a little, I think this might become clearer once we start looking at code and putting things, some numbers to code, you'll see. The third one. Count to 3. 1, 2, 3. N log n, or log n, yeah. So this right here, that's the one term. All right, the next one. 1, 2, 3.
N cubed.
N cubed, good. Now the last one's always tricky. I want to know what people think about this one.
2 raised to
Oh,
n.
2 to the n, yeah, 2 to the n. We don't like that. Oh, but if you start plugging these numbers in to a calculator, you might get surprised, but more on that one later. Okay, so how do we get T of n in the first place? That was all very abstract. What does this all mean for you as programmers? Obviously you want better functions, but what is, like, show me a function and tell me how to get those numbers from the function. Like, that's all great, but if I don't know how to do that, all we have to do, and I'm going to tell you something. I say there's a lot of, like, be wary of shortcuts in computer science. Like, oh, there's no trick. The one trick is, what does the code say? That does apply here. All we're going to do is count the number of operations being done. That's all we have to do. There's no magic to it. But there are some, like, shortcuts kind of that we can take. They don't always work, but for quick and dirty, quick analysis of what's going on, sometimes there are little, shortcuts not the right word, but tricks. So, we just spent all this time going from T of n to order n. How the heck do we get T of n? Let's look at some code. So, how much stuff is being done? There's no trick question here. How many units of work are being done? 3, 4, this one's kind of hairy, right? Because I guess it depends, like, well, is one line of code a unit of work? For our life at this stage, let's not call it a line of code, but like, oh, creating the variable x and assigning the value 0 to it is 1 unit. I suppose there could be an argument for that third line of code being like, well, we have to add x and y and then create the variable and assign it there. Fine, but for simplicity, I might call this T of n 3, because it looks like there's like 3-ish things going on, right? But remember, we're lazy computer scientists, and I don't like T of n. I want to know what the big O of this is. What's the answer? 1. It's not n. Now you might be scratching, but let me show you an example with n. I don't know why I'm freaking out there. Have a look at this code. Try to come up with the T of n. How much work is being done here in total? Well, okay. Let's slow it down and think. That very first line of code, that's clearly like one thing. Okay, so we've got that one thing. But then we've got this chunk underneath. So 1 plus the chunk underneath. Now what's this chunk underneath? Well, there's a loop here, but hold on. Let's skip the fact that there's a loop. What is the inside of the loop? How much work is being done on the inside of that loop?
1.
Just 1. But how many times am I going to do that one thing of work? How do you know it's n?
0 to
Because the loops is go to like 0 to n minus 1. Yes?
So then does that mean that with nested loops, it would be like n squared and so forth?
Maybe we'll just sit tight. So this is it. We're doing 1 unit of work n times. That's the loop. Oh, and then plus the 1 at the beginning. Right? Now don't get, a lot of people, they start thinking too hard about, like, well, how do I know when it's a plus and when it's a multiply? Multiply is like, well, how many times are you doing? Remember how multiply is like times? Right? That's the trick. How many times am I doing that one thing in the middle? Well, n times. So multiply. But you add each step to each other. But like, we could think of the loop as 1 plus 1 plus 1, but how many plus 1s do I have? I didn't know that most. We just put the multiply in there. End of the day, this one looks like it's going to be 1 plus n, which of course means this has a big O of what? N. Yes?
So int I equal to 0 and those assignments does not consider in the calculation? Inside the for loop for initialization int I equal to 0.
Yeah, I suppose maybe I could have counted them, but they're not really important at this stage. It's just a loop going this many times. You've got a good point though, where it's like, well, maybe it should have been like, well, the setup, we have to create that and do that. Yeah, I'm lazy.
Okay.
You should be too. nested loops. This one can get hairy, but it's not really a trick to it. So, what do we have here? Well, let's go all the way inside. Let's go inside the loop first. Okay? How much work is being done on that one line of code in like the middle there? Y equals y minus 1. Like how much work is being done there? Well, it's like that one line of code, every time it gets run, it's going to be like 1 unit of work. But of course, there's a for loop there, right? So we've got this like 1 unit of work. But then there's that for loop. And how many times is that for loop going to run? Well, that for loop is going to run n times, right? However, now we also have that x equals x plus 1. That one line of code, how much work is that there? So we have to like do plus 1, right? So we've got that y equals y minus 1 times n, because that loop's going to run n times. Oh, and we've got that one extra line of code above it. Great. But of course, how many times is this being run? N, because that outside for loop. Right? It's going to be like that. And then of course we've got that x equals 0 at the top. How much work is that?
1.
Alright, let's just add 1 in. Well, there we go. That looks like, I guess that's a reasonable-ish t of n. I want to like multiply that n in there, and we get something that looks like that. N squared plus n plus 1. But of course, we're lazy computer scientists. I want big O. Big O, this is what? 1, 2, 3?
N squared.
N squared. You're pros. Look at this. N squared. Yes.
Why didn't we go from the top?
I mean, we could have. It's just, I think it's kind of easier the other way. But if we start at the top, it would be the same thing. It's just, it's easier to think of like, because otherwise we'd be like, okay, 1 plus, well, we're going to do n things, but what's being done? And I just find it easier to work outside than inside. But do whatever you want. Other questions? N squared. So, imagine I've got this. Try to think of the big O. Don't worry about T of n. What's big O? Talk amongst yourselves so you can figure it out. I've got x equals x plus 1. That's 1 unit of work. But how many times is that loop going to run?
N by 2.
1/2 n times n divided by 2. Yeah, it's all the same stuff. It's all 1/2 times n. Right? That's how many times that loop's going to run. But of course, what do we say about coefficients? What?
Ignore.
With more vigor.
Ignore.
Doesn't matter, we don't care, cut them. This means it's order what?
N.
N. Still order n. Yes.
Why is it
1 over 2n? Well, because that loop goes from 0 to n. But what are we counting by? By 2. Right? So if we want to go to 10, if I was counting by 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's 10. But if I'm counting by 2, 0, 2, 4, 6, 8. So I'm doing half the number of things by counting by 2. Answer your question? Yeah. Cool. Now the next one's a little tricky. Think about this one. Take your time with it. Chat with each other, scratch some stuff down on a piece of paper. What's big O of this? All right, raise your hand if you think you know. What do you say in the back?
Square root n.
Square root n. No. But I like where your head's at. Anyone else want to give it a go?
1 over n squared.
1 over n squared? No. I like what you're thinking though. 1 over n squared. That's like the same thing, right?
Oh, is it?
No, it's
Square, oh, square, yeah. What are you thinking?
log n.
Log base 2 n. Why?
Because honestly, I don't know. I thought abstractly that's what it would be.
You're like, it's probably that one. Yeah. Good. Can anyone tell me why?
Because it's incrementing by 2s, like it's constantly being multiplied by 2.
That's ultimately why, but let's break that down. He's like, well, because we're multiplying by 2 every time. Yes, but let's make sure everyone follows. So, let's say n happens to be, I don't know, a nice round number of 1,024. Don't ask too many questions about why I picked that number. Let's say this was linear, right? If this was linear, and this loop just incremented by 1 every time, how many times would this run? 1,024, and yeah, of course. Now, let's say we're doing this multiplied by 2 every time, and I start at 1. Okay? So 1. Is 1 less than 1,024?
Yes.
Someone say no. I'm pretty sure someone just said no, but okay, anyways. Of course it is. So we do it, whatever, and then we double it. Great. We double it. We double it. Oh. Well, I guess we don't do 1024 in our case. How many times did that run? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. 10. It only ran 10 times. Because it's almost as if I took this number and was like dividing by 2 every time, right? I mean, it's like we're binding it at one end or the other. I can go this way and double or go this way and divide, right? And the question then, like, if we're doubling that way or if we're dividing, because if we're doubling every time, you might start to think like, oh, 2 to the something. But remember, like, although that's happening, it's 2 to the something, but we've got an end, and we're rapidly moving towards that end. So the amount of times we're going to run is going to be like rapidly decreasing relative to like the plus plus. Someone do me a big favor. Who has Google readily available? Here's what I want you to type into Google. Log _2 space 1024.
10.
10! Huh, it's convenient. How many more times would this loop run if I double this to 2048? How many more times would I run this?
One more time.
One more.
Only one more, but I literally doubled it. There's 1,000 more things there. But yet, I still only have one more thing to do because I'll double it again down here. I run out of space. But if this was linear and I doubled it, how much more work would there be?
1000.
Twice as much work. But when it's log, it's only one more. Isn't that interesting? Did you say wow? I know, right? Yeah.
So then, shouldn't log base 2 do less work than n?
Absolutely.
I thought in the other diagram it did more work.
You probably saw n log n.
Oh yeah.
N times log n. Let me make sure I'm not crazy. Because if it does show that, that's wrong. Yeah. N log n. Yeah, good call. So, we saw two different implementations of stack. Stacks are pretty efficient. But what's better? Here's pop from a linked stack. What's the computational complexity of this? Anyone have a knee-jerk answer? N? Why N?
You're adding the stack, I guess. Yes.
You're wrong. Yeah. 1. We just created a new, we just removed, by the way, it's a pop, so we're not adding to a stack. But we're popping, we just removed one thing, whatever. How about the array stacked pop? What's the computational complexity of this one? 1. Yeah. One of the tricks is look for loops. Loops kind of show you, oh, this is going to be related to something. So, regardless of the implementation, pop is like order 1. That's pretty good, actually. Now, we're going to look at queues soon, and we get a little bit of a difference. Stacks are pretty good in general. Push. Here's a push for a linked stack. What's the computational complexity of this? On the count of 3. 1, 2, 3. 1. Constant. It doesn't matter how big the stack is. Every time I push something, still 1. But what about this one? N squared. Ooh, that would be bad if it's true. Thank goodness it's not. Yeah, so you're saying, well, expand capacity. It's constant unless we have to expand capacity. Now remember, I ranted about this before when I was talking about the amortized computation time. It's always order 1 until we have to expand capacity. And expand capacity, what's the computational complexity of expand capacity? N, right? Because I might have to double it and then copy all the things over. And well, how many things do I have to copy? Well, that's what's N, right? So the amount of work there depends on N. But of course, I did tell you about amortization. But in reality, we do know that at the end of the day, which one did kind of technically seem to be better computationally? The linked one, right? Because no matter what, the push and pop were linear. No, constant. Not linear, constant. Where the array stack, the pop was constant, but the push was mostly constant, but there might be that linear thing. But we amortize it, but you know. Now, based on this, of course, which implementation is faster for your computers?
The arrays.
Raise your hand if you say linked. Really high, I want to see. You are so wrong. Okay, now, let me explain something. The speed of these operations for a computational system, absolutely, the linked one, we know it's going to be better. However, we can't ignore the computational system that we're using. You are all using a laptop that's going to be the exact same computational system. But all of these algorithms that I've defined here, we, people have defined, they can be executed by a lot of different types of computational systems. I know we wrote it in C++ for these computers, but I could give it to a group of students to execute bubble sort to sort themselves, right? If I gave you the algorithm for bubble sort, you could probably figure out how to sort the whole class by height, for example, right? Now, but the trick here is the computational system, just one sec. The computational system we're using just so happens to be engineered in such a way that it's really good and quick with arrays. So even though there's those expand capacities, the computers that we're using to do all our computer science, it's faster with the arrays. But it's really important to note, that's a consequence of the computational system you're using. You don't need to be doing that. Your computational system could be you with a piece of paper and a pencil. It could be your cells in your body doing what it does in order to keep you alive. Computational systems, computers, are much more than those boxes you've got in front of you. So, the speed is the amount of computation taking place is for the algorithms and how they are implemented, but it's kind of like independent of the computational system. Once we consider the computational system, there's more variables at play that we have to account for. But a lot of times in computer science, we really make a big effort to try to abstract away from specific computing systems, because it's important for us to understand these things in terms of computability, how much stuff is being done and all that. You got a question?
Yeah. When there's like if statements and stuff like that, do you and like say the if statement contains like a loop or something like that? Would you base the amount of work that, like when you're writing the amount of work that needs to be done? Do you base that?
There's more on that later. For Big O, you always think like worst case scenario.
Okay.
Yeah.
Cool.
All right. I'll see you. There is lab today. I won't be there. Just come up after. Yeah. Cool.